This talk is about somatosensory evoked potentials, technical issues. It will be conducted in a question and answer format. The first question is, the EEG machine and the somatosensory evoked potential machine have exactly the same components. A true, B false. This is a colorful, cartoonish blueprint representation of the modern EEG machine. The modern EEG and EP machines have many things in common, but they are not exactly the same. To begin with, preamplifiers are a need for evoked potentials and less so for EEG. We can appreciate the reason for this by looking at this table from Jasper Clinical Neurophysiology book, which lists the different voltages of the signal surveyed by different clinical neurophysiological exams. Notice that the EEG records electrical activity with a voltage ranging from 1 to 2000 microvolts, whereas somatosensory evoked potentials record electrical activity of 0.1 to 20 microvolts. So you can see why preamplifiers that are mere single-ended amplifiers placed in front of the differential amplifier are needed to monitor evoked potentials. But what really makes the evoked potential machine significantly different from an EEG machine is the computer. The computer, in addition to having a ADC converter, numerical low and high frequency filters, a discrete to continuous converter, and a screen. It also has an internal mechanism that triggers a stimulus and matches time with the stimulus in order to acquire data in a relatively small time period that would allow for us to accumulate that data and summate it. So one trial can add to another, and so on, in order to average the signal. So the answer to this question is false. Next question. Electrode impedance should be less than 5000 amps. A true, B false. This diagram represents a single-ended amplifier. These amplifiers are used as preamplifiers before the differential amplifier and are also used after the differential amplifier. Single-ended amplifiers are used for one purpose only, and that is to boost voltage. Preamplifiers are the first real evoked potential machine elements that make connections with the electrode. Electrode impedance for somatosensory evoked potential, as for EEG recording, should be between 5000 and 100 ohms. Some authors list less than 10,000 ohms as acceptable limits for high electrode impedance. All authors agree that impedance should be about the same in all electrodes, some mentioning that all electrodes' impedance should be within 20% of each other. So the answer to this question is false. Next question. The minimum amplifier input impedance must be A. 10 mega ohms, B. 10 milliohms, C. 1 ohm, D. 5,000 ohms. At the point of entry of the nervous system generated electrical activity to the preamplifier, indicated here by the magenta arrows, impedance needs to be very high. In Chiapa's book, the number quoted is more than 10 million ohms. Others, including the Academy guidelines, say that it should be 100 million ohms or more. So the answer to this question is A. Next question. Nervous system electrical output captured by electrodes will generate recordable waves without outside added electrical energy. A true, B false. To answer this question, I will use an analogy that works for me and I hope it works for you. This analogy has three actors: a dropper half full of gas, a gallon of gas, and a car. I will start by drawing a brain. I could have chosen any other part of the nervous system because the principle is about the same everywhere in the nervous system, but the brain will do. Let's say that the brain produces electrical activity with an energy equivalent to a dropper half full of gas during a certain amount of time. Now on your right, I have added a gallon of gas poured from a gas pumping station during the same period of time as it took for the brain to produce the half dropper full of gas. If we put in the car the gas from the dropper, the car will not go. If we put the gallon, it will go, let's say 20 miles. The story is about the same with the Vogue potential machine. Neuronal power alone, that is the energy generated by the brain, cannot get the EP machine working. The Vogue potential machine, in order to work, needs energy from sources other than the nervous system. Usually, the energy comes from an electric outlet. So the answer to this question is false. Next question. What is the amplification factor in this example? Please take a few seconds to look at it and then try to come with the correct answer. The choices are A. 1,000, B. 10,000, C. 100,000, D. 1 million. The amplification factor or gain of an amplifier can be figured out by simple mathematical operation. This operation consists of dividing the output voltage by the input voltage. Conducting this operation, we get 1,000. So the gain in this amplifier is 1,000. Notice that 1,000 has no units, and that is because since the same unit is present on both sides of the division, they cancel each other. So the answer to this question is A. Next question. 1 microvolt amplified by a million joules voltage. A1, B10, C100, D1000. This diagram casts the question. The first step to solve this operation is to convert microvolts to volts. So 1 microvolt is equal to 1/1,000,000 of a volt. You then multiply it by the amplification factor, which in this case is 1,000,000, and you get 1 volt. So the answer to this question is A. Next question. Somatosensory evoked potentials require amplification of A. 5,000 to 25,000, B. 25,000 to 50,000, C. 50,000 to 70,000, D. 100,000 to 500,000. Chiappa's book states that the amplification factor needed for somatosensory evoked potential is from 100,000 to 500,000. Remember that the usual voltage being recorded during somatosensory evoked potential ranges from 0.1 to 20 microvolts, as we have previously mentioned. For pattern shift visual evoked potentials, the gain needed is less. It is in the range of 20,000 to 100,000. This is so because the potential generated by pattern visual evoked potential is much larger. It is in the range of 1 to 200 microvolts. The recommended amplification for brain stem evoked responses is from 200,000 to 500,000. The need for a higher low limit of amplification is because the amplitude of the brainstem wave are from 0.1 to 2 microvolts. That is smaller than the amplitude of the waves evaluated during somatosensory evoked potentials. The amplification needed for EEG ranges from 100,000 to 1,000,000. The amplitude of the electrical activity recorded during EEG ranges from 1 to 2,000 microvolts. It is important to remember that all these values given are not agreed by all, and some books may show a slight variation, but in general they tend to hold. So the answer to this question is D. Next question. Which of the following characterizes a good single-ended amplifier? A. Adequate bandwidth, B. Low noise, C. Amplitude linearity, D. All of the above. Single-ended amplifiers have one function. That function is to boost electrical activity. Electricity in the United States has 120 volts, but transformer, one of the initial elements of the EP machine, dropped the voltage. So by the time electricity reaches the preamplifiers, the voltage is usually around 10 volts. Be it as it may, electrical energy from an outside source provides energy for the single-ended amplifier to amplify the electrical activity coming from the brain. Simple-ended amplifiers should have certain qualities that makes them acceptable for somatosensory evoked potential testing. They must have an adequate bandwidth, which for somatosensory evoked potential is defined by the American Clinical Neurophysiology Society as allowing to pass activity between 0.1 Hz to 500 Hz, losing less than 30% of their amplitude. They must produce little noise. They must have good amplitude linearity. If a wave entering an amplifier is 0.1 microvolt and leave the amplifier as 1 microvolt, then a wave coming into the amplifier as 0.1 millivolts has to come out as 1 millivolt. The other quality single-ended amplifiers must have is that they should have good phase linearity. This implies that if a peak of a 1 Hz wave measuring 20 microvolts is shifted 2 milliseconds to the right, the peak of a 2 Hz wave measuring 50 volts should also be shifted 2 milliseconds to the right. So the answer to this question is D. Next question. During their operational range, good simple-ended amplifiers provide an output signal that has a direct linear relationship to the input. A true, B false. This line represents input voltage. As you can see, some of the input voltage have a negative sign on your left, and on the right there is no sign. The absence of sign implies positivity. So as you can figure out, these signs are related to polarity. Now I have added a vertical line that represents output voltage. In this case, as with the input voltage, the negative signs are present and the positive signs are omitted. I will use this figure at this junction to talk to you about gain, which expresses the relation between the input voltage and the output voltage. So the relation between input and output voltage is called gain, and in this case we're looking at a gain of 20,000, which correlates with a gain of 86 dB. So in other words, we can either talk about a gain of 20,000 or a gain of 86 dB. Now I have represented with the blue line, which I have just introduced, the relation between output voltage and input voltage and gain. So a negative 150 microvolts input will produce an output voltage of negative 3 volts, and an input voltage of positive 100 microvolts will produce an output voltage of 2 volts. And a positive input of 150 microvolts will produce an output of 3 volts, as you can see in this frame. I like this definition of gain. Gain refers to an increase in amplitude of the action potential or any bioelectrical activity, may I add, that occurs as a result of electronic amplification. So the answer to this question is A. Next question. Gain and sensitivity are the same thing. A true, B false. To answer this question, I will go back to the chart that we used to answer the last question, but I will add one more element. That element is trace amplitude. Trace amplitude refers to the vertical displacement of a signal as a result of voltage, which I have introduced to this figure using yellow script. As you can see, trace amplitude is displayed here in millimeters. The negative sign in this case indicates down displacement. The lack of a sign indicates upward displacement. Now I have added the same blue line I had used to answer the past question. This line indicates the relation of a gain of 20,000 on the input and output voltages. I have done so to show you the relation between input voltage, output voltage, gain, and sensitivity. So if we have an input of negative 100 microvolts, to which we apply a gain of 20,000, we end up with 2 volts. That is 2 negative volts, which corresponds to a vertical upward displacement of 10 millimeters. I have now added to the chart a sensitivity of 10 microvolts per millimeter. If again we take a negative 100 microvolt input voltage and divide it by the sensitivity, which we have just expressed, the result is a vertical upward displacement of 10 millimeters. And if we are provided with a given displacement, let's say to follow the same example with an upward displacement of 10 millimeters, that is a wave of negative 10 millimeters, if we know the sensitivity of the equipment, which in this case is 10 microvolts per millimeter, we can obviously arrive to the conclusion as to how much voltage is in the wave. In this case, it is quite obvious that the voltage will be 100 microvolts. In this frame, I have added another example, but this time using a positive 50 microvolts input. I will not go through it, but if you have any questions, stop the video and work it out. The bottom line is that if you know the input voltage, in order to figure out the displacement given the gain, you multiply. If on the other hand you're given the sensitivity, you divide. And if you know the displacement and the sensitivity being used, which is usually the case in most clinical neurophysiology testing, what you need to do is just multiply. I will now go and take away some elements in this chart to show you what would happen when we change the sensitivity and the gain. Indicated by the arrow, you can see the gain of 20,000 and the sensitivity of 10 microvolts per millimeter. And now in this new frame, I have changed the gain to 40,000 and the sensitivity to 5 microvolts per millimeter. You can also see that as a consequence, the slope of the blue line has also changed. I have done so to match the changes being presented in the gain and in the sensitivity. As you can see, a negative 100 microvolt produces an upward displacement of 20 millimeters, and were we to know the displacement, that is 20 millimeters up, we can figure out the input voltage. Once again, I want to show you this definition. Gain refers to an increase in amplitude due to electronic amplification. Sensitivity refers to a display in resolution. Please take a few seconds to look at this definition and read it. So the answer to this question is B. Next question. Within their operational range, amplifiers provide an output signal that has a direct linear relation to the input signal. A true, B false. I hope by now you are familiar with this figure. In this case, I am displaying a slope consistent with a gain of 20,000 and a sensitivity of 10 microvolts per millimeter. A good single-ended amplifier maintains the same relation between input and output voltages within the operational range of the amplifier. A bad single-ended amplifier does not. As you can see in this example, the solid line at the top right corner represents the function of a bad amplifier. The intermittent line shows how a good amplifier should work. Notice that an increase of 50 microvolts in the input voltage corresponds to 1 volt increase in the output voltage. And this is maintained throughout all the segments, but it is not maintained in the segment on the top right, where you can see that at a higher input voltage, the same increase, which is 50 microvolts, produces a much smaller increase in voltage than in all the other segments of equal size. So the answer to this question is A. Next question. Which of the following values corresponds to an amplifier with 20 dB gain? A. In 1 microvolt to out 10 microvolts. B. In 5 volts to out 50 volts. C. In 50 microvolts to out 500 microvolts. D. All of the above. dB is a funny unit. It has a different connotation when used for voltage than when used for power. When referring to neurodiagnostic testing, it is usually used for voltage, but this is not so all the time. So 20 dB gain corresponds to 10 times an increase or a gain of 10 times. In this frame, I have expressed gain ratio as a function of out and in voltage. On the right, the gain is 10, and on the left, the gain is 100. I have in this frame highlighted in magenta 10 microvolts out to 1 microvolt in, which represents a gain of 10. Just as 500 microvolts out to 50 microvolts in corresponds to 10, and therefore they both can be described as having a gain of 20 dB. Now, if you look at the other column, an output of 500 volts resulting from 5 volts input represents a gain of 100, which can be expressed in dB as 40 dB. So the answer to this question is D. Next question. Conversion to dB is easy when the gain ratio starts with 1. A true, B false. This diagram can be used to visualize the relation between voltage ratio, gain, and decibel conversion. When the first number in the amplification ratio is 1, the way to translate it to dB is easy. Just count the number of zeros and multiply them by 2, and then add a 0 at the end to the result. So when going from 1 microvolt to 10 microvolts, you have 1 0. So multiply the 1 by 2 and add a 0 at the end. And as you can see, the answer is 20 dB. I will give you another example. If the input is 5 volts and the output is 500 volts, the amplification ratio or gain is 100. So 2 multiplied by 2 is 4, and when a 0 is added, it results in 40. I do not know whether this rule stands for huge numbers, but it works for most of the numbers that I have tried. So the answer to this question is true. Next question. Guidelines from the Academy use dB in relation to voltage to talk about common rejection mode, but use it in relation to power when describing bandpass. A true, B false. The question that you're answering is not meant to increase confusion, merely to help you understand the guidelines from the American Society of Clinical Neurophysiology. In this frame, I have put a segment of those guidelines. I like to call your attention regarding common rejection mode, that is a quality of differential amplifier to which I will refer later on in this talk, but for now, I just want you to look at the numbers. Here, the numbers are 80 dB, which corresponds to a ratio of 10,000 to 1 volt. So here the dB is used in relation to voltage, and as you can see, 80 dB corresponds to a ratio of 10,000 to 1. In the next sentence, the guidelines talk about bandpass, and they use the term -3 dB. This time they are using dB as it relates to power. So 3 dB corresponds to a 2 to 1 ratio, which implies doubling the initial number. The minus sign in this case implies that it's the inverse, though it means 1 to 2 ratio, which is half of 1. So since voltage is the square of power, and here we are talking about -3 dB, which is equal to half the power, the voltage described in this statement is 1/2 the square of power, which is 70%. So the bottom line is that no wave with a frequency between the numbers given should drop by more than 70%. So the answer to this question is true. Next question. As the sensitivity is increased, the wave becomes larger. True or false? In this frame, you can see a wave at different amplifications and the corresponding sensitivity. If you electronically amplify a wave, that is, if you increase the gain of a signal, you are making the signal bigger because more voltage is going into the wave. If you increase the sensitivity of a wave, you will pack more voltage in each millimeter, and therefore you will need less millimeter to represent a given amplitude. So as the sensitivity of an amplifier is increased, let's say from 5 microvolts per millimeter to 50 microvolts per millimeter, the wave becomes smaller. This is the opposite for gain. The higher the gain applied to a given input voltage, the taller the wave will be at the output. So the answer to this question is B. Next question. Averaging is a form of amplification. A true, B false. This is a column of event-related potentials stacked one on top of the other. There are 16 potentials. Notice that in the legend, the vertical line corresponds to 40 microvolts. Averaging them in groups of 4 double the amplitude. Notice the legend. Further averaging those 4 will produce an even larger potential, since those activities that are equal will become bigger because they will add each other, whereas the activity that is not equal will subtract from each other. Again, notice the legend. Here the vertical line, despite being the same size, represents 10 microvolts instead of 40 and 20 as it did before. This degree of amplification has been achieved by going from 16 potentials to 4 potentials and from 4 potentials to 1 potential. I will label this exercise as trial 1. Now let's imagine that we do the same and label the new trial 2. We do it again and label the trial 3. And we do it again and label the trial 4. As you can see, now that we add these 4 potentials, the result will also be in amplification. In this frame, the vertical line in the last potential is 5 microvolts. The potential, as you have seen, it has become larger, and therefore the legend indicating the vertical line has gone to 5, as we just have mentioned. Normally, a second independent bunch of trials is conducted to confirm the fidelity of the recording, and this is confirmed by demonstrating their replicability. In this frame, we have added both trials in order to see replicability, and as you can see, it is there. Both are interposed and are rather similar. So the answer to this question is A. Next question. The purpose of neuronal activity amplification and manipulation in the current EEG and EP machines is to provide the electronic circuits with enough voltage, 1 to 10 volts, to fulfill the energy needs of the analog to digital converter and other elements of the machine. A true, B false. Reading this sentence will answer this question. The need for amplification is to provide the necessary electrical activity in order to make the different elements of the EEG and evoked potential machine work. So the answer to this question is A. Next question. Amplification of a signal can be the only step to visualize nervous system generated electrical activity. A true, B false. I am going back to the analog that I used at the very beginning, which included a dropper half full of gas, a gallon of gas, and a car. Here, car 1 is fueled only by the gas in the half full dropper that we describe as coming from the brain at a specific time. And as you can see, such an amount of gas will not make the car go. Car 2 is fueled by a gallon of gas, which will go 20 miles. Car number 3 is fueled by the gas in the gallon and also by the gas in the dropper, and this car will advance 20 miles and 1 millimeter. Now let's bring a crane and transport car 2 and car 3 1,000 times the distance that they have traveled. So now car 2 will be displaced 20,000 miles and car 3 will be displaced 20,000 miles and 1 meter. The 1 millimeter more that car 3 moved at the beginning is now 1 meter. 1 millimeter is difficult to see, but 1 meter is easy to see. So using pure amplification, it is possible to visualize brain waves. This frame shows some drawings and writing by Hans Berger that were presented in Dr. Pierce Glore translation of his works. That is the translation of the work of Dr. Berger. As you can see, this was recorded in 1924. Certainly at that time, there were only single-ended amplifiers, since differential amplifiers were invented in 1932. So the answer to this question is A. Next question. Somatosensory evoked potentials require amplifiers with amplitude linearity to accommodate input signals with peak-to-peak amplitude of A. 1 microvolt to 10 microvolts, B. 5 microvolts to 100 microvolt, C. 5 microvolt to 500 microvolts, D. 0.1 microvolt to 20 microvolts. In this frame, I have introduced a y-axis representing frequency, and it extends from 0.1 Hz to 100 kilohertz. And now I have introduced an x-axis indicating voltage in microvolts and millivolts. The recommendation by the society is that amplifiers used for evoked potential should maintain an amplitude linearity for amplitudes between 5 and 50 microvolts. These guidelines do not specify for the type of evoked potential being studied. The recommendation stated by Jasper Clinical Neurophysiology is for amplifiers to be able to maintain linearity in the case of somatosensory evoked potentials between 0.1 to 20 microvolts. So the answer to this question is D. Next question. Amplifier used for somatosensory evoked potential require bandwidth to accommodate input signals ranging from A. 0.1 Hz to 100 kHz, B. 100 Hz to 10 kHz, C. 0.1 Hz to 30 kHz, D. 0.1 Hz to 3 kHz. This is the same chart that I have just used to answer the last question. The bandwidth suggested by the Academy that needs accommodation includes frequencies from 0.1 Hz to 5000 Hz. It is understood that the implication is that this wave will be reduced by less than 30% of their amplitude. Jasper Clinical Neurophysiology suggests a narrower bandpass of 20 Hz to 3 kHz. So the answer to this question is D. Next question. Which of the following comments about noise is not true? A. The wider the bandwidth, the more the noise. C. Can be defined differently by different authors. C. With a bandpass of 0.1 to 5000 Hz, amplifier noise should not exceed 2 millivolts RMS. D. An electrophysiological device, when turned on but not connected to a patient, does not make noise. In Cooper's EEG technology, noise is defined as the fluctuations in output signal that occur even in the absence of input signal. In Levin and Luther's comprehensive clinical neurophysiology textbooks, a much wider definition is used. In this book, noise is defined as an unwanted or extraneous signal that interferes with signal being studied. I like to think of noise as intrinsic to the equipment. In this group, I lump noises due to flowing current fluctuations, and also I include in this group those noises that occur as a consequence of thermal agitation of electrons in different elements of the electrodiagnostic machine, which occur even in the absence of flowing current. So intrinsic currents can be divided in two groups: those that occur when the electrons are flowing and those that occur when the electrons are not flowing. But there's also another type of noise which is extrinsic to the machine. In this group, I include those created by electric components that are away from the EEG machine. So they are reaction of the EEG machine either to electric or magnetic fields produced usually by electricity. Regarding what level of it is tolerant or should be tolerated, in 2006, on the guidelines produced by the Academy regarding evoked potentials, the acceptable level of noise of an amplifier was not to exceed 2 microvolts root mean square. The guidelines for recording EEG on digital media are also presented in this figure, and as you can see, the quoted number is less than 2 microvolts peak to peak. And in a similar guidelines 10 years later, that is in 2016, the recommendation was changed to less than 1 microvolt peak to peak. As important as the difference number are, I like to call your attention to two other important points in this frame. The first of this point is the unit use. Notice that in the 9A guidelines, that is the guideline for evoked potentials, the units used was RMS, whereas in guideline 8 and 4, the unit use was peak to peak. The implication of the different unit use is easily appreciated by looking at this frame. The magenta arrow represents root mean square. The aqua arrow represents peak to peak. As you can see, peak to peak is more or less 2.8 times bigger than RMS. The second point I like you to notice in this frame is the bandwidth. As you can see, in the case of evoked potential, the bandwidth allowed is much wider than the bandwidth allowed for EEG. And remember that the wider the bandwidth, the more the noise. So the answer to this question is C. Next question. Common mode rejection ratio of differential amplifier used for EP at least should be A. 1000 to 1 60 dB, B. 10,000 to 1 80 dB, C. 100,000 to 1 100 dB, D. 1 million to 1 120 dB. Common mode rejection, that is the ratio of the amount of activity of similar quality that should be rejected to the amount that is being kept, should be at least 10,000 to 1 or 80 dBs. So the answer to this question is B. Next question. Which of the following is not true regarding somatosensory evoked potentials? A. The time resolution of the analog to digital converter of 20 microseconds is appropriate. B. The amplitude resolution provided by a 12-bit analog to digital converter is optimal. C. The system should allow averaging at least 4,000 trials. D. An SSEP study should have at least 2 channels. A specification for analog to digital converter and a screen representation for somatosensory evoked potential vary greatly. The analysis time, that is the time the analog to digital converter should make binary numbers from the activity arriving to it and store it, should last from 50 to 200 milliseconds. It is appropriate to do it for 50 when it comes to upper extremity, but for lower extremity 200 milliseconds is more appropriate. The appropriate sampling rate and sampling interval of the analog to digital converter for somatosensory evoked potential is a matter of debate. The apparent conclusion presented in the second edition of Electrodiagnostic Medicine is, as far as I can surmise, that a sampling rate of 12,500 per second and a sampling interval of 80 microseconds is good. Nevertheless, In this regard, the recommendation from the Academy is that the time resolution of a system used for evoked potential should be 20 microseconds or less. If we take into account that the maximal amplitude of somatosensory evoked potential is 20 microvolts, then a dynamic range of plus or minus 10.2 microvolts will suffice. This can be achieved with an analog to digital converter of 12 bits, which yield an amplitude resolution of 0.005 microvolts. The only recommendations I could find about the screen is that it should have more than 500 pixels per channel, and that the screen should have the capability to display at least 4 channels. So the answer to this question is D. Thank you very much for your attention.